All right, in this final video, after section 6.4, we can call it the last video of 6.4, but really its purpose is to compare very closely the differences in different use cases for discs or washers versus shells. So I've said it in a bunch of my videos. Discs and washers really are the same thing. So let's go ahead and just write that down. So a washer, so this is just a couple preliminary things. So first of all, a washer is essentially, we can conceptually think of it as the same thing as a disc. A washer is essentially two discs being subtracted from one another. So in this way, we mean, so this is one disk. Okay, I'm going to say that this disk has a larger radius. So I'll call this the outer radius. And then another disk here, but this disk has a smaller radius, so we'll call this the inner radius. So if we do outer radius minus inner radius, right? If we do, if we do big disk minus little disk, then this is equal to a washer. More or less, if I were a better artist. So here we can see it. We've got a inner radius, and then we also have a outer radius. So in this case, our shaded region is really something like that. So that's why we group them together. So think of them as the same thing. In fact, there's one other thing we can say, and that is a disk is just a washer with an inner radius, so Ri of 0. So it's an inner radius, it's a washer. So a disk is just a washer if it has, let's say, with an inner radius Ri of 0. Okay. Let's go ahead and do some comparisons here. So what I would say is, make a little table here. Let's go ahead and say we have disk/washers, and then down here we will have shells. So for disks and washers, if you are rotating, so there's my symbol for rotate. If we're rotating about a horizontal axis, then you would integrate with respect to the horizontal variable. So this would look something like dx. So what's important here is that you have dx. But if we're rotating about a vertical variable, vertical axis, then our formula is pi times the integral of a to b radius squared dy. So what's really important here is this tells you that you need your integrand. If this is dx, then this means this function r must be sorry, this radius r must be a function of x. So this tells us r must be a function of x. Similarly, this one tells us that r must be expressed as a function of y. You can't have any x's in that. Shells is exactly the opposite. So the volume here is 2 pi integral from a to b, let's say. This would be the radius times the height. This would be with respect to y. And again, this means that each r needs to be a function of y, and h needs to be a function of y. Over here, we've got 2 pi integral from a to b. Again, r times h dx, if we're rotating about a vertical axis. So again, it's saying the radius must be a function of x and the height must be a function of x. So, okay. To me, these are the things that I have to look at when I am looking at a region. If I'm looking at a region, these are the things that I would talk about. So here's an example. Let's say I've got a region that looks sort of like this. Let's say I'm more symmetric too. Let's say something like that. I'm trying to make this like intersect at the right point so it looks symmetric, which can be kind of hard to do when you're doing something freehand. So let's use this as a guideline. There we go. That looks better now. Okay, so if we do something like this, let's say we're going to rotate this about, I don't know, let's say we're going to rotate this about some vertical axis, let's say. So if we're going to rotate this about a vertical axis, then using shell method would be better. Why is that? Because you draw a slice perpendicular, or excuse me, parallel to the axis of rotation. And then if you consider this distance, this represents your radius, and then the length of this segment represents the height. So if I'm going to assume that each of these expressions here are given as a function of x. So if they're given as a function of x, so let's say y equals this, then it's easier to use the shell method, because for shell method, rotating about a vertical axis, you can leave your radius and height in terms of functions of x. So if you are given a problem where the curves that you're working with, the functions you're working with, if they are presented to you as a function of x, so something like, maybe y equals x squared minus 4x plus 1. I don't know. I'm just making something up. This is presented as a function of x. This right here, y equals, let's say, 3x, that is presented as a function of x, but it's very easy and quick, it's trivial even, to solve for x. So an example like these two right here, although one is presented as a function of x, the other is presented as a function of y, they are easy enough to algebraically manipulate. It's like a one-liner. Doesn't require any thought, doesn't require any sophisticated techniques. There's no completing the square. There's no plus or minuses. There's nothing like that. It's just a quick Algebra 1 solve that you can do in your head. In those cases, it doesn't really matter if it's presented as a function of x or a function of y, because you can interchange them so easily. So really what it boils down to in a problem is you want to look at your more complicated functions, such as like a quadratic or maybe a cubic if you had it, or sine of x or something like that. Something where it's not always easy and straightforward to solve for the other variable. If your functions are complicated in the sense that I just described, and they're given to you as a function of x, then that sort of tells you at this table you want to be probably thinking to use one of these two methods. Because if your functions are complicated and they're presented as a function of x, that leads you to believe that it's going to be difficult, if not impossible in some cases, to solve for the other variable, to make it a function of y. In those cases, it's probably best you stick with being able to leave your functions in terms of x. So that kind of tells you either you're going to use disks and washers, and that would be the case if you are rotating about a horizontal. If you're rotating about a vertical, this would mean shells. If you're, for instance, let's say, so that kind of tells you. If you're rotating about a horizontal, then disks and washers would be it. If you're rotating about a vertical axis, then shells would be what you want to do. So for me, I sketch my region, and then I look at my functions to determine which one is more complicated. That being said, there is the example over here in this previous page that we did in the previous video where my functions, this is the only function besides this axis here, and I guess these two lines, these were the only things that we were given. This is extremely easy to solve for the other variable. So my functions aren't complicated here, but it would definitely be better to use disks or washers in this example instead of the shell method that the problem asked us to use. So it's not just are your functions complicated. That's one layer of understanding. That's one strategy here, is to examine how complicated your functions are, and is it even possible to solve for the inverse? It may not be. But another perspective to have is look at the geometry in your problem. For shell method, you always draw a slice parallel to your axis of rotation. So if I draw a slice here, I notice that below this dotted line that I have, the slice here has this function as its left boundary, and it has this line as a right boundary. But above this dotted line, if I draw a slice parallel to my axis of rotation, then this slice, the left boundary, is again the same line as before, but now it's this boundary here. So this tells me that I would have to use two integrals. Okay, so you should be thinking of your slices, and does that mean that your boundary, what's on the left, what's on the right, what's on the top, what's on the bottom, do they flip-flop at any point in your region? If they flip-flop, then that might mean it is probably better to integrate it in the other way. But there are examples of regions that flip-flop no matter what you do, in which case you really do need two or more integrals to find the volume no matter what. So really, I think there's like this algebraic perspective of looking at how complicated is your equation. Is it even feasible or plausible or possible to solve for the other variable? Also, examine your geometry. So in this example over here that I started off with, shell method makes sense because no matter where you draw the slice, the same function is on top and the same function is on the bottom. It doesn't matter where you draw that slice. They never flip-flop or change to something else. So shell method is easy, straightforward. That being said, if we consider the disk and washer method, for instance, if I use, it would be a washer because our region of integration, our area that we're rotating about the axis, is this area here. So there's this gap between where our area is and where our axis of rotation is. Because there's this gap, that means there is going to be a hole in our solid at some place, so that means it's a washer, because the cross-section of that would be a washer. So for washers and discs, we always draw a slice parallel, or excuse me, perpendicular. I always flip-flop for some reason until I say it out loud. You always draw a slice perpendicular to your axis of rotation. So right here, if I think about this, whatever the x value is here, this would be your inner radius, and this x value over here would be your outer radius. So if I consider drawing my slice at some arbitrary y value, then we would have to figure this this x value out. At this arbitrary y value, what is the x value? Well, the x value here would be whatever the inverse function is. So this would be f inverse of y. Similarly, over here, this would also be f inverse of y. But the x values aren't the same thing. And why is that? It's because this function here is not a function of y, because it fails the horizontal line test. If I look at one input value, there is exactly two output values. So this means the inverse would have a branch. It would have two different pieces. They would split. So there would be a branch. And I can call this like branch 1. I'll do a subscript of 1. This would be branch 2. Really, it would split right here at the top, because at this y value at the top, there is only one output for this one input of y. If we plug in this y value, then there's only one. So really, the inverse is split right here. So the 1/2 would be this inverse function. The other half would be this inverse function. So we really have like a left branch and a right branch. So immediately you can see that this is going to be difficult because I have to find the inverse function. So that immediately tells you that this is probably not the way you want to go. Furthermore, not only is it a pain because you have to solve that for the inverse, also notice that our region here, this area, if I draw this line in the middle here, if I happen to draw my slice, my representative slice, I just drew it arbitrarily above, but if I draw my slice down here, look at what happens. So I'm just trying to clean this up a little bit. If I draw my slice down here, then it's not going to be f inverse, the left branch and the right branch of f inverse. It's going to be the left and right hand branches of y inverse. Or I mean g inverse, excuse me. I don't know why I can't talk today. So not only would you have to find inverse functions and decide which branch to use where, you also would have to do two separate integrals because your integrand changes. So washers would be a very, 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 very bad choice. So there's an algebraic component. There's also a geometric component.